The next speaker is Mykola Dedushenko from CMITS, and he's going to talk about two-part Derived CFT. Please.
Okay. Okay, thank you for inviting me to this event. It's really the biggest conference I've ever been to, in terms of size at least, and quite an impressive event. So indeed, this talk, titled Towards Derived CFT, is actually it's about the work in progress and some wild speculations, but a lot of it is work in progress with, writing a paper with Grekov, who is a student at Stony Brook and soon moving to Japan. And there are some important references here. A lot of it is based on the paper of Kapranov that appeared in 2021. These guys also had a supersymmetric generalization of Kapranov's work, but we don't really use this paper, but I wanted to mention it because it's one of the only follow-ups on Kapranov's work that exists so far in the literature. So here's the plan. I'll start by introduction and some speculations, then I will talk about conformal geometry and ambitwister approach to understanding holomorphic conformal manifolds, and describe some computations and our hopes for the future. So introduction. What do I mean by derived symmetry? Well, the notion of derived symmetry exists in math literature. It's mostly, it's various papers by people working in derived algebraic geometry, but I think the only papers that actually call them derived symmetries are papers by Will Donovan, at least the only ones that I could find. And the idea is that you have, in math, the idea is to look at the autoequivalences of the derived category of coherent sheaves on X. So let's say you have some space X, you can consider just category of coherent sheaves and its autoequivalences. That would be your ordinary symmetries plus some irrelevant junk. But once you go to extend to the derived category of coherent sheaves, you get, and look at it, autoequivalences, you get something more interesting. This derived symmetry group, derived symmetry algebra, which you don't have to understand the details of that. For our purposes, is roughly some device, which is differential graded Lie algebra, that unifies symmetries and deformations of X. In this case, these are deformations of complex structure and some other deformations. So the general expectation that you could sort of have is that derived symmetries of some structure S is a certain differential graded Lie algebra. So it's a Lie algebra with also differential, right, and graded. So it's a cochain complex, which also has a Lie bracket, which unifies sort of symmetries and deformations of your structure S. But what does it mean for physics, or for example, for QFT? Well, one could hope that there may be some further generalization of symmetries, which would call derived symmetries, which unify symmetries and deformations of some kind of structure. Like, for example, let's consider usual flavor symmetry. So invertible and zero form, so not like a higher form and non-invertible stuff from previous talk. Actually, okay, in previous talk you don't have any higher form, but then let's just go look at the ordinary old symmetry. What does it mean to have a symmetry group? Well, it means that you can couple your theory to the background G gauge field, right? So in case of continuous symmetries, you literally have principal G bundle that you couple to, and in this case, this bundle is our structure, sort of S that I had on the previous slide, or we could call it the symmetry structure. So symmetries and in this case, you could be looking at the symmetries and deformations of this principal G bundle, or actually G bundle with connection, right? Because this is the background gauge field. So in simple terms, there's a background gauge field, and symmetries are sort of gauge transformations that preserve it, and deformations are just deformations of this background gauge field, right? So one could, for example, if we have a trivial bundle, with a zero gauge field, then the symmetries are just gauge transformations that preserve the zero gauge field. These are just constant gauge transformations, which is your standard usual global symmetries. And then deformations are basically you introduce small background gauge field and look at the response of your quantum system to this gauge field, which was determined by the current. Now, exists recent work where people study how some general features of how CFT responds to such introduction of such background gauge field. But in general, no one looked at like what happens if there's symmetries and deformations, if they have some kind of algebraic structure. But it's natural, for example, in CFT to expect such algebraic structure because it would be encoded in the operator product expansion of a current with itself, right? But in that example, of course, it's a sort of speculation because I didn't give you any construction yet. In that speculation, the symmetries were acting fiber-wise on your principal bundle. You can also allow them to act on your base, in which case you get space-time symmetries, and the structure involves some geometric data on M. For example, if you're looking at Poincare symmetry, the corresponding geometric data is the Euclidean structure, so flat metric, that you can look at now at symmetries, and you can also look at deformations of this flat metric. Today, I'm specifically interested in conformal symmetry and conformal structure. Yes? Yeah. Sorry. Well, I'm not talking about gauge symmetry here, just global symmetry. But you're allowed to turn on the background gauge field and look at what happens, how your system responds to it. Well, the statement was that first there's this idea from math of derived symmetry, which unifies symmetry and deformation. And now I'm trying to look at like what would be the physical context for it. First, I'm sort of like let's say the first example is flavor symmetry, like global internal symmetry, which I'm not studying in the rest of this talk, but I just sort of give it as an example that something would be useful to study later, like in the future, right? It's not a gauge. Symmetry is a global symmetry for which you understand as an ability to turn on the background gauge field. Then the symmetry is transformations that preserve this background gauge field, and deformations are just deformations of this background gauge field. Right? And there must be some algebraic structure, which in the CFT would in principle be encoded in the current OP. Right? In 2D CFT, you would just get a fine symmetry. Yes? Yeah, well, yeah, so that would be in the case of conformal symmetry, the simplest example, because in that case, you will have no deformations, just symmetry in 2D. So, okay, so now I will not go as fast here because now it's the main subject will be conformal symmetry. So I'm interested in conformal structure on your space-time. So by conformal structure, I mean metric. So on your space-time, and metric defined up to modulo the equivalence of like modulo Weyl transformations. Then in this case, symmetries are, of course, diffeomorphisms that preserve this G, which is your usual conformal transformations. And deformations will be metric variations up to Weyl transformations. So together they should form some kind of derived conformal symmetry. And both symmetries, but we know that both symmetries and deformations are encoded in the stress energy tensor. We construct conserved charges for space-time symmetries from the stress energy tensor, but also stress energy tensor it's a response to the metric variations. So again, we expect that the algebra physically should be encoded in some sort of TTOP. But in larger than 2 space-time dimensions, it's kind of hard to decode this algebra. Like there's some various, like it's clearly related to these subjects of BMS algebras or generalized BMS, or even more further generalization, the light ray algebra, which contains all these inside. people cited in the literature. There were also some other attempts to extract algebra from the stress energy tensor OP in higher dimensions, but like nothing looks like the most general answer, so which clearly sort of extracts all the data you can extract. So instead of doing that, we'll use alternative algebra geometric approach by Kapranov from that work that I mentioned earlier, and then try to use that as a guiding sort of principle. So that I'll start by some small review of conformal geometry. So as I mentioned, so by conformal manifold, I mean Riemannian manifold them with Riemannian metric or pseudo Riemannian metric defined up to scale, right? And then, as I mentioned before, conformal symmetries are diffeomorphisms that preserve this. At the level of vector field, it means that as you act with the lead derivative on your metric, you get something proportional to the metric. Okay? And then the classical fact, which is the Liouville theorem, is that in higher than 2 dimensions, if you take conformal transformations of some open subset of RD, or maybe RD without a point, you get just a finite dimensional group, which is O D plus 1 comma D. Whereas in 2 dimensions, you get, of course, infinite conformal symmetry, Virasoro symmetry. Right, then, so here, just repeat this fact. Now, where does the infinite dimensionality go when you move from 2 to higher dimensions? Yes, the question? Oh, okay. So what happens to this whole infinite dimensionality? Well, it goes, so what Kapranov proposes in that paper, or maybe answers, is that it goes into deformations. So in 2 dimensions, you have infinite many symmetries and no deformations. As you go up, say to 3D or 4D or higher, you get only finite many symmetries, but then instead you get infinitely many possible deformations of your metric. And here I'm simply referring to the fact that in 2D, every metric up to a wild transformation is just it's locally flat, right? Whereas in higher dimensions, it's not the case. So then what we need is we want to construct some kind of a differential graded Lie algebra, which he calls this R-conf, so as a differential graded Lie algebra, it's a cochain complex. So there's a differential, there's Lie bracket, and then the 0th cohomology matches with conformal symmetry, whereas the first cohomology of that cochain complex contains deformations. So, and that's what is the derived conformal algebra. Now, before I proceed, let me just mention that these worlds of conformal field theories and holomorphic field theories, they only overlap in 2 dimensions. Like here, there's this little tail corresponds to 1D because in principle we can have they're somewhat subtle. You can have CFTs in 1D. So, but if we go outside of 2D, I mean they're just 2 different kind of things. People have been studying these a lot recently, especially like people like Brian Williams, Ingmar Saberi, and others. And in that case, you also find some kind of derived or higher versions of symmetries. But this is not what we're interested in. I'm interested in this, in actual physical CFTs, and try to see where we can go here. So, but still, it is useful to actually analytically continue and use a holomorphic language. But I just want to emphasize that we are here. So by analytic continuation, I mean that will extend Rn, where our theory lives, to Cn, and use tools of complex geometry. Of course, we know that one cannot analytically continue QFT all the way to Cn. There's you encounter various singularities along the way, which have been known for a long time, but recently, for example, there's this notion of, what is it called? Allowable metrics, right? By Kontsevich, and Witten, right? So you can only analytically continue to a certain extent. But one can still study real conformal geometry of Rn in terms of holomorphic conformal geometry of Cn. So just at the level of geometry, it's okay to do it. Just and that will be my sort of perspective. So in real setting, it's also important to consider Rn with the point removed, because that's where we insert local operators. When we insert local operators, we can For example, we may allow metric deformations that have sort of singularity at that point. Removing point in Rn corresponds to removing solutions to this equation. So after analytic continuation, this will be generalized to the whole null cone sitting at the origin. So after analytic continuation to Cn, it means I also need to consider such space where Cn with a null cone removed. So Cn, so these are two important spaces, Cn and Cn with null cone removed. Now, if I wanted to consider extended operators like land operators or surface operators, then I would need also more complicated geometry. But let's just focus on local operators for today. So, so now we view these spaces Cn and Cn with a null cone removed as holomorphic conformal manifolds. But more generally, by holomorphic conformal manifold, I mean complex manifold M with the conformal class of holomorphic metrics. So again, holomorphic metric up to wild transformations. And by holomorphic metric, I mean something like dz squared, as opposed to dz bar on C. And then holomorphic conformal maps are holomorphic diffeomorphisms that preserve this holomorphic conformal metric. Another important example of conformal quadratic is a conformal quadratic, which will not be, I mean, it is actually important in computations, but I will not emphasize this detail. But just to give you an example, you can consider a quadratic hypersurface in CPn+1, and you will get another important example of holomorphic conformal manifold, which is just a complexification of the sphere of a Sen. And then its conformal group, in this case, is O(n+2), C. And which also sort of illustrated the Liouville theorem that I mentioned before in the real setting. It just extends verbatim to homomorphic setting. So we need to, for now, we need to quantify symmetries and deformations of this holomorphic conformal structure. And that's that's where the ambit twister technology enters, because it will be the tool that will help us do that in a natural and unambiguous way. So this holomorphic conformal geometry was studied a lot, especially there are some works by Claude Lebrun, who studied holomorphic conformal geometry on M in terms of the space of null geodesics on M. So back then he didn't call it that, but nowadays it's called ambit twister space. I think it was also introduced before this space, before Lebrun, but I couldn't find the source, actually, the origin of this name, ambit twister space. The earliest paper I could find, some papers by Mason and Skinner, well, already they write it as if it's like a common name, but I couldn't find the source of the name, ambit twister space. So if someone knows, please let me know. But anyways, it's the space of null geodesics on M, where by null geodesic I mean holomorphic curves which obey your geodesic equation, but it's just that you now your proper time, you think of it as a complex variable, and then they are null. So which is just this condition that the tangent vector is null, or it's clear that null geodesics they only depend on the conformal class of the metric, not on metric itself. Well, we can understand it if you think for a second, and then in fact the geometry of this space, it encodes everything you need to know about the conformal geometry of your original space. And especially it's important that this space is holomorphic contact. It's a contact manifold, but a sort of homomorphic version of a contact manifold. Now, what's a contact manifold? Just I will briefly remind you. Of what? Dimensional? It's actually 2n minus 3. Yes. No, let's say dimension of M is, the complex dimension of M is n. Then the complex dimension of L of M is 2n minus 3. So what is contact manifold? What is contact geometry? Well, it's basically the odd dimensional analog of symplectic geometry. Right? So here there's a picture. You have, first let's look at the real contact manifold, just as a reminder. So we have odd dimensional manifold, and it's equipped with distribution theta, which is just a collection of two m-dimensional, so codimension 1 subspaces in each tangent space. And it's maximally non-integrable in the sense which I will explain in 10 seconds. But so it also has a contact form, which is just this projection from your tangent space to the quotient by this distribution. So, and then the kernel of this contact form is your distribution. And then the fact that it's maximally non-integrable means basically that this contact form has, if you form the top form from it in this way, you get the non-degenerate volume form. So it's a generalization of symplectic geometry in the sense that d theta, it kind of looks like symplectic form on this 2m-dimensional distribution. And then there's this Reed vector field, which points in this direction, which is determined as it lies in the kernel of d theta, and its normalization is fixed usually like this. Now this thing has a holomorphic analog, where all you do is now you say that now you take manifold of odd complex dimension. It has complex codimension 1 distribution in the holomorphic tangent bundle. Now in this case, this quotient is actually a non-trivial line bundle over X, and theta now is a 1,0 form valued in this line bundle, and d theta is going to be 2,0 form. And well, now the non-integrability condition, it means that you construct such volume form, and it's again a non-zero, but now it has to be actually a section of canonical bundle times kappa to the appropriate power, because this is the power of how many thetas you have here. So now the statement is that the space of null geodesics is in fact holomorphic contact. Actually, are there any questions? Because maybe I moved too fast. Okay. So the space of null geodesics is holomorphic contact. One can understand the contact structure in the following way. If you're given a null geodesic gamma, which is the point of your space, then the tangent vector is just some small variation of your geodesic, right? And then you say that this variation belongs to the contact distribution if this condition holds. So if product of tangent vector and this variation is 0. So this statement, this determines the contact structure. And well, another reminder, which actually should belongs to the previous slide, but I really didn't have space on the previous slide, is the notion of Legendrian submanifold. So on a compact manifold X, you can have a Legendrian submanifold, which is a m-dimensional submanifold, such that all its tangent spaces belong to the distribution. So it's sort of the analog of Lagrangian submanifolds in symplectic geometry. Now, in this case, you can define, for ambit Whistler space, you can define Lx is a collection of all null geodesics that pass through the point X. All these null geodesics, they form a certain subspace in your ambit Whistler space, and that actually is a Lagrangian submanifold in L of M. And well, so you see that points on your original space, they correspond to Lagrangian submanifolds of L of M. And in fact, one of the results that can be extracted from Lebrun's works is that, like, basically all Lagrangian all the Legendrian submanifolds of L of M are of this form. So they correspond to points of your original space. Okay, here actually, I just gave all these dimensions that what you asked before. So if your M has dimension n, the L of M is here. I'm talking about complex dimensions. It's 2n minus 3-dimensional. All right. So, and another important fact is that if you have 2 points of your original space that are null separated, then the corresponding L of x's, they intersect, which is sort of easy to understand. The intersection points would correspond to null geodesics that pass through both x and y. All right. So the statement of this Lebrun I call it Lebrun correspondence is that the conformal geometry of M and captured by contact geometry of L of M. In particular, if you have conformal transformations at the level of your space-time, such that point x1 goes to x2, they correspond to contact transformations in the ambit tracer space, which map Legendre and submanifold. So in particular, this means that conformal symmetries of your original M correspond to contactomorphisms of L of M, so contact transformations. And then another important thing is that deformations of conformal structure of M correspond to deformations of contact structure. So deformations of L of M as a holomorphic contact manifold. This will be important for us. Any questions so far? M? Oh, yes. Right. So since I have complexified everything, so your usual 2D CFT, it's actually C2 here now. So it's n equals 2, right? Corresponds to like your ordinary. Right. So that's like in this case, the Legendre and submanifold is just a point. And yeah, and it doesn't make sense to go below that. So these contact transformations that are symmetries of your M are actually, so what are they? They are generated by contact vector fields. Here's the property of a contact vector field. It means that you take Lie derivative of your contact form with respect to the contact vector field, and you get something proportional to the contact form. And in fact, curious thing about this contact geometry is that they are in one-to-one correspondence to contact Hamiltonians, which can be obtained by just contracting the contact vector field with theta, which is sort of unlike in symplectic geometry, because there, if you take, it's not one-to-one, right? Because in symplectic geometry, if you take constant Hamiltonian, you get zero vector field. So there's some kernel. Here is literally one-to-one in the contact case. So, so the symmetries correspond to, so this contact transformations, they are in one-to-one correspondence with contact Hamiltonians, which are, in fact, holomorphic sections of that bundle that I mentioned previously. So symmetries can be viewed as holomorphic sections of that bundle, or zeroth cohomology over sheaf of holomorphic sections of that bundle, right? But then, once we have this description of symmetries, oh yeah, I also forgot to mention that there is also a Lie bracket. There's an actual Lie bracket here, which is the sort of the Poisson bracket of this contact Hamiltonians, which is basically defined like this. You take a contact vector field, you take the commutator, and you plug it back into the contact form. This bracket thus endows H0 with a Lie bracket, and this is how you get back your usual conformal symmetries in this context. Right? So you get zeroth cohomology with the Lie bracket. Now, if you've ever seen anything heard anything about deformation theory, then your natural expectation would be that deformations should sit in the first cohomology. All right? Complex dimension, yes. Greater or equal than 2, yes. No, as I said, some previous slide, I complexified everything. So C2, if I take C2 for M, it will be one of the easiest examples. That's where you get Virasoro. Because like the real physics lives on the real slice of, so it's on, so everything is doubled. So we expect that deformations are in H1. So what are the deformations? Well, it means that you deform this contact structure, you deform the distribution, and the deformation of distribution is captured by deformation of the contact 1 form. And well, okay, you can fix certain freedom of diffeomorphisms and choice of trivialization of kappa, such that this deformation is a 0,1 form. So recall that theta is a 1,0 form. It is possible to choose to fix all these freedoms such that delta theta is a 0,1 form. And then at the linear level, the conditions on this deformation, which basically that it determines a complex structure and complex structure is integrable, they're all encapsulated in the fact that it's actually that this delta theta belongs to the first Dolbeau cohomology. At the full nonlinear level, you actually get what you would expect, the Maurer-Cartan equation, just like in the BCOV theory. And in fact, there's a corresponding deformation of complex structure that is accompanied by delta theta, which just obeys the Kadar-Spencer equation. Now, the bracket here is what I mentioned before, is this contact bracket, sort of the version of Poisson bracket in the context of contact geometry. Now, in our examples that we'll consider later, there will be no high cohomology, so there will be no obstructions. There's only H0 and H1. Now, in the approach of Kapranov, all you need to do now is to take derived sections of this bundle. So, and then you naturally get the derived conformal group. So what does it mean? Well, first I mentioned also that since kappa, there's this Poisson bracket, the sections they have a Lie bracket. So kappa is really a sheaf of Lie algebras. But once you pass to the derived sections, you automatically get a differential graded Lie algebra. There are various ways to understand this. Perhaps the simplest conceptually is to use the Dolbeau complex as a model for this DGLA. So you simply take Dolbeau complex with so 0, p forms with values in kappa. As a differential, you take del bar, and you can check that the contact bracket, it actually extends to 0, p forms, and it obeys the Leibniz rule. So this is literally your DGLA. There actually exists other possible models, like something called Thom-Sullivan construction, which can be useful for various purposes, but you can think of in terms of Dolbeau. So this is what I mean by derived sections. So you, instead of just taking sections, you take the cochain complex, whose cohomology computes your sheaf cohomology for kappa. And then, well, because kappa has this Lie bracket, this thing also has a Lie bracket, and there's a differential compatible with it. So, yes? Sorry, say again. This equation. Oh, I mean, this is at the full nonlinear level, right? So it's a finite deformations. But when you think of a DGLA, the algebra, you think of it only infinitesimal deformations. So in that case, you forget about the bracket and just look at the cohomology. Well, I mean, I mean, the whole construction, of course, also involves, so that's why I mentioned that there's no high cohomology here. It means that this deformation theory is unobstructed and everything is captured by H1. But in this construction, I mean, if you have high cohomology, you just have them. So it's all sort of automatically included. All right, so just to emphasize again, we have this device, the DGLA RCOM, whose zeroth cohomology is your usual conformal group or conformal algebra. Deformations are H1 in H1. And then there's also bracket, which in principle, at the level of cohomology, acts like this. But if you only look at this at the level of cohomology, you lose a lot of data because when you think of RConf up to quasi-isomorphism, so like as an object of the derived category, it carries much more information. So when you think of it in terms of chain complexes, that's what, when you work at the derived level, it has much more data in it. And I will say more on this in a bit. Okay, so now let's turn to some computations and examples. So let me start with a warm-up example, which people already asked a few times about, which is the 2D case. In the 2D case, again, because I complexified everything, I'm actually looking at C2. The ambitwister space, in this case, is just a disjoint union of two lines, complex lines. Because basically, you have null geodesics like this in 2D and like this. So these form one collection parameterized by C, these form another collection parameterized by C. And if you remove the null cone from C2, then in the corresponding ambitwister space, you simply remove 0 from each of the C's. So the contact bundle here in this case is just a trivial bundle, O, and the contact form is just DZ on C. So everything is topologically very boring. If you look at the conformal symmetry, so I'm looking at the zeroth cohomology of this sheaf of homomorphic forms, of homomorphic functions, then for two C's, Z and Z tilde, just like polymorphic coordinates. Sorry, I meant this is. Yeah. Everything is polymorphic. It's like you can. I mean, we often do in physics. We complexify things and then we treat Z and Z bar as actually holomorphic variables in some extended space. But then on the real slice, they're complex conjugate to each other. Right? Right. Yes. Oh, at the geometric level, you can, of course, don't see central charges. Because so really, it's not Virasoro, it's really with algebra without central charge. But then, and when they study quantum theory, you get central charge. Right. So if I look at this and take cohomology, so all I have is just this, right? So basically, holomorphic vector fields on one CFT and another, and you identified as with half of Virasoro. Well, if I look at the space with the null cone removed, then you'll get back the full Virasoro, or rather with algebra, because there's no central charge. And this is, of course, something that you all know, because when there's no insertion at the origin, you just have vacuum. You get only half of sort of Virasoro in this case. And as I said previously, in 2D case, there are no deformations. So first and high cohomology is all 0. So okay, we get back the usual Virasoro symmetry in this case, in 2D. Now, the main example for me is actually 3D. Now, in this case, the ambitwister space is the total space of O1 plus O1 over CP1. Topologically, it's a trivial bound. So topologically, it's just CP1 cross R4. But I mean, holomorphically, there's some structure here. And it's somehow it actually coincides with the usual twister space, well, or rather like open. Okay, if you compactify it, you get CP3. And another main example is C3, where you remove the null cone, in which case the corresponding ambit-Rister space is, again, the total space of this bundle, but with a zero section removed. In both cases, the line bundle in which the contact form is valued is simply O2 on the base, pulled back to the total space. Okay, so in this case, we compute cohomology, and quite expectedly, H0 is just your usual conformal group, or everything is complexified, so the signature doesn't matter. So just SO5 from a C, conformal group in 3D. In both C3 and C3 without null cone. Now, if we look at the deformations, then in this case, well, of course, first of all, we get deformations because we're above 2 dimensions. There are deformations. And the deformations for C3, for unpunctured and punctured case, are slightly different. For here we get some V, which I will explain what it is in a second, and here we get V plus V dual. So V, it parameterizes deformations of conformal structure on C3, which are regular everywhere. Whereas V dual contains all deformations that are singular along the null cone. And they are actually, so this V is a certain infinite dimensional irreducible representation of conformal group. And V is dual representation. And then there's no high cohomology in this case either, as I already mentioned earlier. So then the bracket structure in this case is, so first of all, there's a non-zero Lie bracket here, which is just your usual Lie bracket on conformal algebra. And here the bracket boils down to the representation structure. So it's just the data of how SO5 acts on this representation and on its dual. The bracket between V and V star is 0, well, because there's no high cohomology, otherwise it would be sending us into H2. But we can, because they are dual, we can add a central charge by hands in this case, if we want to, we can say in the quantum case. So this is the algebra at the level of cohomology, but as I said, there's more data if you work at the level of DGLA. One can actually, given the deformation of contact structure, which is in H1, one can compute back the variation of the metric using the ambit-Rister version of Penrose transform, which is I'll sketch it here, but it might be a little bit confusing, at least it was for me. So first you look at the map, the following map. So let's say Q is the quadric of null directions in a tangent space, and M is your original space. Then there's a natural map rho to the ambit-Rister space, which you take the point in M, you take the null direction, and you consider null geodesic that goes through X in this direction. That's a natural map rho. It turns out that once you take a pullback of this bundle kappa here upstairs, the cohomology upstairs vanishes, so the pullback of this 0,1 form is actually d bar or something else. And then upstairs there's an operator D, which is a vector field generating this geodesic flow, the flow in the null direction. And then once you apply this D to J, you get some object which in turn encodes your metric. Well, here P's are coordinates along the fibers. So if it's confusing, don't stress too much about it. I'm just mentioning it to say that one can compute the metric variation given the cohomology class. In particular, for this real, for the regular, non-singular variations. Well, actually, I'm going to give you explicitly the cohomology classes, just sort of like, let's say that U and V are coordinates in the fibers of this O1 plus O1, and Z is a coordinate on the base, on P1. Then the elements here are represented by certain differential forms. So these are like analogs of our half of Virasoro. Now they have more indices, but they like certain Dolbeault forms that represent these cohomology classes. And one can check by computation that they're really in the cohomology. And then the ones here are represented by somewhat different differential forms. And like you can notice that here, sort of the non-trivial part is on the base, whereas here, the non-trivial part is in the fiber. And these things, they actually correspond precisely to cohomology classes in the punctured C2. Well, but one can perform this ambitwisted transform and then just get explicitly the metric variations. Again, these are some, so it's of course written in a certain gauge, but there's some metric variation, which are some polynomial expressions for regular variations. For singular variations, they're a bit trickier to compute. I'm only giving here the L000 example, which you see. It's a certain variation which has singularity along the null cone. But here the full data is sort of still under, we still haven't finished this computation, so it's a work in progress. Now, okay, now suppose we have this, we computed this differential graded Lie algebra, this derived conformal symmetry. So what does it act on in general CFT? There's an obvious problem that generic CFT has no natural choice for differential. So what's derived about it? Of course, you can think, there's sort of a natural grading, which is conformal dimension. Like that's the only quantum number that's present in every CFT. Well, okay, there's also rotations, but like spins, but there's really no natural differential. So instead, what we propose is that instead of working with the GLA, let's replace it by the sort of its related L infinity algebra. So what I mean here? Well, okay, so L infinity quasi-isomorphic L infinity algebra, so it's a proper technical term. And then this such L infinity version should act in the CFT. So as a reminder, or for those who never heard about it, but probably everyone has, L infinity structure is basically a generalization of Lie algebra, where you have, in addition to your usual binary bracket, you also have a differential. And when do I finish? What time is it? 5 minutes. Oh, okay, good. So in addition to your binary bracket, you also have differential and higher brackets, and there are some consistency conditions between them, basically, that the Jacobi identity is violated up to higher brackets, and so on. And it is well known that if you have a differential graded Lie algebra, then at the level of cohomology, you induce this sort of L infinity structure with vanishing differential. And they sort of, in derived category, they contain the same amount of information. So, so if I pass from the GLA to its corresponding L infinity algebra, this structure captures as much data as the GLA itself. And higher brackets in the cohomology, they basically capture this missing information. Now, how do you get it? Well, again, a brief review of a homotopy transfer. Let's say that this is our GLA, this is cohomology. One need these three maps. First, I, which basically for each cohomology class you write its representative. There's a P, which projects back on the cohomology, so gets rid of stuff that's not in the cohomology. And then there's H, homotopy, such that this condition is obeyed. So this is called deformation retract, and sometimes people also impose additional simplifying conditions, which is called contraction. Well, anyway, so given this data, you can generate brackets in the cohomology, which are represented in sums over rooted trees. For example, the binary bracket in the cohomology now is written like this. You take elements in the cohomology, you embed them by I into your DGLA. Here, this trivalent vertex corresponds to taking the commutator, the binary operation in here, and then you project it back in the cohomology. That's your binary bracket in the cohomology. But then you can also, you also have higher operations where on the internal vertices you insert H, this homotopy. So it sort of acts like a propagator in Feynman diagrams. Here's an example of fourth order bracket and so on. Now, Okay, the computing this part is also work in progress. But one thing I want to note is that because n-ary bracket, it actually has homological degree 2 minus n, it means that since we only have H0 and H1, we expect the n-ary brackets between the following spaces. You either have two H0s and the rest are H1s, and it maps into H0, or you have one H0, n minus 1 H1, so it maps to H1. So we expect to have these higher brackets that will capture the missing data. And then the hope is that in physical theory, now this should be obtainable from the stress energy tensor OP. So let me remind you that metric perturbations, they are generated by stress energy tensor. So to the first order, let's say I have operator O inserted at the origin, and then I have this metric deformation, which I contract with the stress energy tensor and integrate over the space-time. Let me also assume that metric deformation is homogeneous of degree Q in coordinates. At least that's the case for deformations that naturally appear from that cohomological computation. Then I can rewrite it as follows. I consider this metric deformation at unit sphere, and I take out the radius dependence outside. And also I do the same to the stress energy tensor. I address it by a dilatation operator, and I compute it only at the unit sphere. So after that, I can write it like this. So here you have a part which is integration over the unit sphere, and then there's some other part which basically stretches it along the rest of space-time. So I can focus on this part, which is metric perturbation localized along the unit sphere, and say that this is the operator corresponding to metric perturbation along the unit sphere, and the way it acts on your sort of local operator or the corresponding state. And such wise, should form an algebra whose structure is captured by the TTOP, but there is still lots of technical difficulties to overcome, such that, well, okay, I will not mention, but just, but that's the natural route. So, and now I will just conclude by saying, and expressing some hopes. So first, this derived symmetry seems to be a new parameter concept in QFT. Like maybe it'll be sort of the further. The last decade has seen a lot of generalization of symmetries, generalized symmetries. Maybe there will be one more step in generalizing. Now, I used this procedure of Kapranov to give a concrete algebra geometric proposal for direct conformal symmetry. And there seems to be a route to find it in physics. As I said, that's work in progress. And then the hope is that the representation theory of this L-infinity version of conformal algebra will hopefully lead to new equations on CFT data, maybe something like minimal model program in 3D and high-D CFT. Of course, it's totally possible that I'm just daydreaming and it's all red herring and nothing will come out of it, but at least I can hope so far. So far, there's no sign that it doesn't work. And then it will also be interesting to work out a similar version for global internal symmetries, something that I sort of alluded to in the beginning in the review, but it was just purely speculation. And then maybe there are corresponding translations for high form and non-invertible symmetries. And that's the end. But, oh wait, hold on a second. There's one more slide. Let's see. So, I hope to see you all next year in Shanghai at Strings 2026. Sure, boundary CFT, another natural generalization, boundary of surface. In this case, I have to, perhaps I could think of surface CFT, right? Then I would have to, instead of a puncture, have to remove the whole surface and consider what it corresponds to on the ambitwister space and classify the deformations. Or maybe there's even some easier way to do it. But yeah, it's naturally part of the story, like one of the generalizations.
M can define on the M with boundary.
Huh?
Our M can define on the M with boundary.
I believe so. I mean, of course, one can think of what happens, or how I should think of geodesics that terminate at the boundary, which I'm not sure actually, but I'm pretty confident that it can be generalized in that direction.
So there should be like, I was just thinking right now, if there should be some notion of extended CFT in this setting of the representation of DGLA. Maybe there's, oh,
Yeah,
okay, thank
perhaps. Yeah.
Hey, hello. Thanks for the very nice talk. That was very interesting. I want to ask about like this. Is there this derived version of Sugawara construction where you could, like these higher conformal symmetries from some kind of current algebra?
I mean, certainly we're very far from getting that, but there must be, right? It sounds interesting, yeah. But yeah, it's very far in the future, right? So one has to work out also the derived version of flavor symmetry that I sort of proposed at the beginning, and then look for possible Sugawara construction in this case.
So do you have examples with obstructed deformations, and have you looked at them?
I don't have them like at the moment, but yeah, there must be examples. Yeah, but I don't know any at the moment, actually.
Any other question? If not the case, let's speak again.